Okay, everybody, grab your coffee. Sorry about that. Now, for question 2.4, you're going to need something like this. It's called a textbook. Okay, this textbook is an SI unit, so that's pretty good. This is a classic textbook here. Right. So we'll come back to the textbook in a minute. Let's have a look at the question. So the question is, we've got this bar thing here. We're pulling it apart, and we want to find out what the maximum stress is. So we've been lying to you. Up to this point, let's say, so we've got this kind of boxy area. What terrible drawing. Okay, so I'm pulling this thing apart, okay? Actually, what the hell is that supposed to be? Right, let's try again. I haven't touched a drop. What are you talking about? Okay, this is a bit better. So, pulling this this square bar apart, right? And so I've got an area 2, which is a big area, and an area 1. I'm applying a force here and here, and I'm saying in this section the stress will be force divided by area 2. In this section the stress will be force divided by area 1. The area 2 here is bigger, which means the stress inside here will be smaller than the stress inside here. And that's it. Well, in actual fact, stress behaves a little bit like streamlines. So you have these what's called stress contours. So the stress kind of goes through the body, and when we get a sharp edge like that, that kind of pushes a lot of these stress contours close together, which means that the stress is actually gets higher than it does in the mean part of the high stress component of the body. So around here we're actually going to get a maximum stress that's bigger than stress 1 in the main part of the body. And how we can work out what that maximum stress is, sometimes that's worked out from FE analysis, sometimes that's analytical solutions, but on the whole what engineers do is they get something called a textbook and they look up the shape they're looking for, and the shape that we're looking for is this kind of sort of bar-y type thing. So it's a flat bar with a bit of a fillet going on there, okay, and that looks a bit like this thing here. So this is being pulled apart, you've got the fillet, so this is the job I want, okay. And the maximum stress will be around this corner part. If I make this corner really sharp, it will shoot up. And you notice we've got these K values here. So that's my stress intensity value. And what I do is I'll take that K value, so notice it starts from, well, it doesn't get to 1, it's always a bit above 1. It starts from, say, 1.2-ish, and it goes up to, say, 3, or usually go up to about 10 or so. Okay, so we're going to look up that table, and when we find the value here, we're going to then multiply it by this one, because that's my maximum stress. But that stress gets even bigger, or rather that's the maximum stress in terms of like these two sections. But stress at that point gets even bigger than this stress. So that's what we're looking for. So how do we do that? Well, we read the question and we get some paper. Right. So I have got to work out the parameters that are relevant in my lookup table. So they should tell me on the table here. You can see it's big D divided by little d. Okay, that matches up with here. We've got a big D and a little d. So the big D divided by little d. Sometimes this might be H, for example, in terms of, whoops, this might be H in terms of heights and things like that. So be careful. But this fine. In this case, it's fine. So the big D is, what's it going to be? So it's not the thickness, it's the widths that we're looking at. So 60 and 40. So 60 divided by 40 equals. Alright, what do you want next? So look at the table. So we've done big D divided by little d. Next thing is in the table is it wants us to work out what R divided by little d is. So R is the radius of the fillet and D is the width of the smaller section. So it wants us to find R divided by little d. So R, the radius of the fillet, is 8 and the smaller fillet is 40. Right, so first thing we want to do is find your calculator and work out those. So 60 divided by 40, 1.5, you'll want to have it in sort of decimals. 8 divided by 40.2. So we've got our numbers. Let's go back to our chart. 0.2 is, I don't want to ruin my book. Right, so 0.2 is here. And the other one is 1.5. 1.5, well, I can't really tell you. It'd be about here, I guess. Which looks like the wrong answer. So what have I done wrong? 0.2. Have I done something wrong? I think I've done something wrong. Let's cheat and look at the textbook. Yeah, it's getting a completely different result to me. 0.2, that's the RD, so that's there. Oh, sorry, yeah. Big D over little d, that's the 1.5, so we want to use this top curve. So we're going all the way up here. Okay, so unfortunately we don't agree with the other textbook. 0.2 and 1.5. Ho hum. Okay, in beer we are getting 1.82, and here it doesn't seem to be right. Rectangle, finger bar, or simple compression. So this one is a bit below. So 1.6, I would say about 1.78. I'm looking at the right things, aren't I? Vertical stress concentration factors. Yeah, okay, so I'm a little bit out from the other textbook, so let's go for 1.8 as being a pretty close value. So K is 1.8. So now I've got my lookup on, and I've looked this up on another chart, and I did get this to be above 1.8. So just a tad above, whereas that book's given me a tad below. It's a bit of a worry. Next thing, we see that we've got the allowable stress. Assume that the allowable normal stress is 165 megapascals. So what else am I going to do? It's not simply okay, so if the maximum stress that I'm allowed to have is 165, I am going to use that stress max equals the K, and because this is put in tension, normally put a sub T there, is going to be that times the average stress for the section which is going to have the highest stress, which will be the smaller section. Okay, so then that means that the smaller section will have 165 megapascals divided by 1.8. So that equals 91.7 megapascals. Okie dokie. Now what do I need to do? So what's the question asking me to do? Determine the largest actual load that can be applied. Okay, so it wants us to find the load. So we found the stress that we can apply in that smaller section. Alright. So in here we know that the stress can be 91.7 megapascals. Okay. So I'm being asked to find the load. So stress is force divided by area. So therefore force is stress times area. I know the stress, 91.7 times 10 to the 6. And now the area, the cross-section area for that section is going to be its height, which is 40 millimeters, times its depth, which is 10 millimeters. So we've got 40 times 10 to the minus 3 times 10 times that to the minus 3. Ready? That should give me my that should be load, which which is a little bit out from their result. So that's F equals 36.7 kilonewtons. So they get 36.3 kilonewtons because they get a slightly bigger stress concentration factor. Okay, so that's what you do for question 2.4.